Hey guys, welcome to the embedded system. Now let's start with this chapter 2. Now in this chapter we'll be looking towards design of an embedded system. So basically there are two types of design approaches: top to down design and bottom to top design. In top to down design, first abstraction is made and we move towards the details of a system, whereas in bottom to top design we consider the details first and move towards the abstraction. The first design, which is top to down design method, is most favored approach, as the abstraction of a system is considered first. That means we think about the system, what should be the functionalities of the system, and then we slowly move towards what should be the components in the system. Right? So let's follow the top to down design approach and let's find out the labels in the top to down approach. So as far as top to down approach of embedded system design, we have 5 levels of abstractions. First, requirement; second, specification; third, architecture; fourth, components; and fifth, system integration. Now let's go and see one by one in details. First is requirements. Now, requirement talks about the inputs, outputs, the functioning, design matrices, which is nothing but the challenges of the system, and then validation of requirements of the finally developed system. Right? So, basically, requirement talks about the definition and the analysis of security systems requirement. It is, I mean, like it should be well defined before the system design starts. So we need to understand the system's requirement very well, and then we'll move towards the next step called as specifications. In specifications, we mainly, designer mainly needs the specifications about the hardware, data types and processing specifications, expected system behavior specifications, constraints of the design, and expected life cycle specifications. For example, in the last lecture we took example in the last lecture we considered a data logger as an example, in which we talked about the requirements first, and the requirement was to sense the temperature and humidity from the environment and send to an internet server. Right? Also, the second requirement was the battery life should long for at least 30 days. So, in the second step, we'll talk about the specifications of the particular device. Now, as far as hardware is concerned, we came to the conclusion that the hardware should be utilized for a particular application was node MCU. Right? Then we need to decide the data types and processing specifications. Whether we are processing the data, whether we are removing the noise present in the samples, should we send the data as it is, or we take the mean of 5 samples and then send the data, right? Those decisions you have to take at the specifications level. Secondly, expected system behavior specifications, right? We have to also talk about, we have to also think about the system's behavior. Also, the constant observed design. Now we discussed that since the analog pins present in the node MCU, right, was limited, that is node MCU is having only one analog input, so that is particularly the constant of a system. That means if we want to add one more analog channel, we won't be able to do that, because node MCU is having only one analog, right? So that is something the constant of a design. Then expected life cycle specifications. We have to understand what is the expected life cycle of a particular device. Are we going to use it for 1 month, 1 year, or like its lifetime? What should be the expected lifetime of a device? That should be considered at the second stage of abstraction called as specifications. Now let's move towards the third level of abstraction called as architecture. Now architecture mainly has two layers. It is called a software architecture layer and hardware architecture layer. In software architecture layer, we can see the three layers. First is architecture layer. The architecture layer deals about the data structure, databases, the algorithm, control functions, state transition functions, processes, data and program flow, right? All those functions are considered in architectural design layer. Then data design layer. In data design layer, the questions are what design of data structure and databases would be most appropriate for a given problem. What data, whether the data is organized as a tree-like structure or should be arranged in like uh, like timeline manner. For example, suppose I want to store the data in sequential manner, I'll go for SQL database. But if I want a time series, that means time stamps at every data, then I'll go for InfluxDB, which is a time series database, right? This is the example. Now the next layer talks about the interface design layer. Now interface design layer talks, I mean, the important question at this stage is like, what shall be the interfaces to integrate the components, right? What should be the interfaces in the design, right? We talked about the engine control unit in our last lectures, and we have seen to control or to communicate between the one model and another model of a same system, we are using CAN bus. And we also talked CAN bus was the like patent of Bosch Industries. So this is a kind of interface between the components, right? So we have to also think about what should be the interfaces between the components, right? So that also needs to be understood. Lastly, hardware architecture. In case of hardware architecture, we have to think about what are the required, what are the required features as far as the hardware is concerned, and we need to understand the architecture of each hardware so that the integration between the hardware will be feasible. Okay, so considering that, now let's move towards the next level of abstraction called as components. Now the component, this is the fourth layer, which is the component level design. The question at this stage should be, what shall be the design of each component, right? And there is also an additional challenge, or I can say the requirement of an embedded system is the optimization of each component as far as memory and the power dissipation is concerned, right? Some typical examples of components are processors, memory, RAM, ROM, peripheral devices, ports, buses, power source or battery management system, right? These are the typical examples of components. So you have to consider these things, and we can then move towards the next level of abstraction called as system integration. Now the system integration talks about the system function and validation. Now this level, this is the top bottommost level, and it like it the fourth layer propagates into the five. So the fourth layer talks about the components. Now components may work fine independently, but when they are integrated, they may not fulfill the design metric. Now what is design metric? In the first layer itself, we talked about the design metric. Design metric is nothing but the challenges we studied in the last lecture. Once we are able to meet the specified challenges in the system, that means we meet the design metric of the system. Now design metric is something kind of a benchmark for a given system. If we are able to achieve that benchmark, that means we are able to fulfill the particular given system metric or design metric, right? So we need to validate our system in the fifth level of abstraction called as system integration for a given design metric. The design metrics may be the power dissipation, performance, process deadlines, user interface size, engineering cost, manufacturing cost, flexibility, prototype development time, time to market, system and user safety, and lastly the maintenance. So a given system or a developed system should be integrated, and then its functions should be validated for a given matrices, right? So after to validate the system, we need to select a proper test so that our system should be validated for the given matrices. So these are the 5 stages or 5 levels of abstraction used for the design of an embedded system. Right. So this is all for this lecture. See you in the next lecture. Bye bye.